welcome to the third session. So we'll start with a presentation given by Julian Giehler from the ONERA. Okay, so Julian.
Yeah, welcome back from the coffee break. I think you can hear me, that's good. I will talk today about bleed systems and how we use them for flow control and particularly for supersonic flows. First, a short introduction, where do we apply bleed systems? So they are usually applied on supersonic air intakes, where, as you know, we have shock boundary layer interactions, and with the shock boundary layer interactions, we have the high risk of flow separation, especially because of the terminal shock, which is always a strong shock boundary layer interaction. And therefore, flow control is required and also applied for supersonic air intakes. And in the past, usually like splitter blades were used so that you have just a gap between the engine and the fuselage. But the problem is you have an extra surface, and nowadays you want to have a lower radar signature, and therefore a promising alternative is the use of a porous bleed system. So you have just here this porous walls. So what's the idea behind? It's very easy. We just want to remove the low momentum flow within the boundary layer. And we do that by placing a cavity below the wall. Then we drill holes in the wall. So we have a perforated plate. And we remove mass from the cavity. And as a consequence, we obtain a transpiration flow through the wall. So upstream of the shock here, where the flow is supersonic, we have a thinning of the boundary layer, or we increase the momentum inside the boundary layer to make it more resistant against adverse pressure gradients. And downstream of the shock, where usually the flow is separated, we just suck the flow separation away. The problem is now, if we really apply a porous bleed system, it consists of hundreds of holes, and one hole is in the size of the displacement signal, so very small in comparison to the whole air intake. And it's too expensive to simulate it, even with run simulation. And therefore, we need models which can be applied as a boundary condition. The problem is with existing models that they often do not consider geometrical variations of the porous bleed. And now is the question, how can we design a porous bleed system if we cannot check what's the influence of the hole diameter, for example? And also many of the models are only defined for supersonic or subsonic flow. But as you know, if we have a shock boundary layer interaction, we have supersonic and subsonic flow, and can we really apply it? And also if we think about separated flow. And my objective for today is, first, I want to highlight or show you, even on a simple case of the supersonic flat plate, that there are some disadvantages with existing boundary conditions. Then I want to illustrate you geometrical parameter influences. So why do we need to consider them in the modeling? And then I will sketch you a way to come to a, I would say, more accurate model. And so I start with talking about model deficiencies. So the typical way of defining a model is, of course, always the same. But I take here the example of the boundary condition of Slater, which is from the NASA and widely used for supersonic air intakes. And what he did, he used only some experimental data from NASA experiments from the 90s. On supersonic turbulent boundary layer bleeding. So you see here the sonic flow coefficient. That's just the bleed mass flow rate normalized by the sonic mass flow rate, which is calculated with the total conditions. Then what you do is, or what everyone does, is try to find a scaling where all the lines collapse. In this case, you just replace the total conditions by the ball conditions, so by static conditions. Then you find a nice regression. Then in some cases, the model is even applied, but there are also some models which are not even applied in the paper. And sometimes you find also a comparison, like here, where you see now that the simulations with the boundary condition do not completely fit the reference data, which is actually a bit strange because you saw that the regression fitted perfectly or almost perfectly. And yeah, therefore I had a closer look. So I performed my own reference simulation where I took all the holes into account. What I did then was that I extracted around the holes all the static properties that I need to compute the model. Then I applied a posteriori the model, and you see it fits quite well. But in the next step, I applied it, and then we see a difference. And what's the reason behind? If we look now to the boundary layer profile, so this is the inflow condition for both cases, no matter if I apply the boundary condition or I'm the reference simulation. I look for the reference simulation, the boundary layer profile downstream of the porous pleat, which is fuller as we increase the momentum in the flow. And now I compare it with the boundary condition. We see that the boundary condition is too effective, so that we increase too much the momentum inside the boundary layer. And this can be also seen here, where it just took the Mach contour fields and plotted the difference. And what we see is that we have an overestimation of the momentum inside the boundary layer. And as a consequence, we obtain, of course, the fuller profile. But on the other side, as we have less or more momentum in the boundary layer, we have also a higher deflection, so a stronger expansion fan at the beginning of the blade, and a bigger pressure drop. And so the pressure is not the same as in the reference simulation. And this is found for all models, so it's not specifically for this model. And our approach now to define a new model was first to perform a parametric study to really understand how the pleat behaves, like for different variations of the geometry. Then we validated our numerical setup with experiments. Then, of course, I tried to find my own regression, and I implemented and tested the model. And I started with the parametric study. So as I told you, it's a very easy academic case. So we have just our supersonic flow at a Mach number of 1.6, a quasi two-dimensional setup. So we use symmetry on front and back. The mesh. Okay. The mesh is fully parameterized, and it's a structured mesh. So we can change the length of the bleed region, the hole diameter, porosity level, thickness of the blade, and also the stagger angle, so the whole orientation. And this is then solved with our in-house solver, ELSA at the ONERA. It's Ballard Almaras QCR turbulence model. And I also will write the inflow in some other simulations that I don't show here, so don't tell you too much. But so how's the flow field looking? This is the flow. The flow comes from the left to the right. At the front of the bleed system, we have an expansion fan as we have a deflection of the flow towards the wall. At the end of the blade, a trailing shock because of the deflection. We can also look inside the holes, and it's exactly the same. We have an expansion fan at the hole and then a barrier shock further downstream. Then we see that we have a huge separated region inside the hole, which is important for the modeling because it limits the vena contracta area and so the bleed mass flow rate. Now, if we look, for example, on the hole diameter effect, I looked on the flow field inside the holes at different positions at the blade or on the blade. So at the first hole, then I move a bit downstream if you go to the second round, and then quite at the end of the bleed region, it's the last row. And from left to the right, the hole diameter is increased. It's always normalized by the hole diameter. And if we look to the sonic line, which is a good characteristic to see how much momentum we have in the flow, you see for the first hole that the smaller the hole diameter, the lower is the flow momentum of the captured flow. In comparison, for large holes, we have a very high flow momentum of the captured hole. If we now move downstream, we see that it looks that the sonic line moves closer to the wall, and we get something like self-similarity. So what we can say is that we have here a strong thinning of the boundary layer, or an increase of the momentum, while here it stays more or less the same. And also interesting is if we look at the stream tube, that we can see that for the small hole diameters, it seems that the stream tube inside the hole is larger. So we have a smaller separated region, so we can extract more mass flow rate. And to plot this, I used also the scaling or the notation of Slater and compared it with its model. The first important note is that we have a variation of the sonic flow coefficient along the blade. So from the first hole to the last hole, the conditions are changing. That's now done for all hole diameters. So we see the trends are not always the same. We did it for different pressure ratios. And in the end, we get a trend for just the mean values that the bigger the hole diameter, the lower is the mass flow rate we can remove, and the higher are the pressure drops, because since we have a higher flow momentum of the captured flow, we have also higher losses because we have the barrier shocks and the underexpanded fans, jets inside the cavity. And this is done now for all the different parameters. And then we see we have some influences which are not considered in this model. And then I wanted to check. And then this was only the global data, but you see here also all the points are the holes. So if we don't look globally on the pore split region, but look on each hole, so we have an even bigger spreading. But now I look on the effectiveness, and therefore I took my inflow boundary layer. I took the boundary layer thickness, displacement thickness, then I removed some mass for the smallest hole, checked that I can decrease my displacement thickness by approximately 50%, so I have more momentum inside the boundary layer. I did the same, extracted the same bleed rate for 1 millimeter holes. Now we see that the displacement thickness is only decreased by approximately 25%. And very interesting now for 4 millimeter, we have some regions where we have even a higher displacement thickness. So we have even a degradation of our boundary layer profile. So maybe we make our flow field worse than it was by removing flow. So it's actually not what we want. We have also huge three-dimensional effects. So here the gray area shows the envelope of the boundary layer profiles along the span. And because it's always a bit hard to look on the boundary layer profiles, especially if you have shock boundary layer interactions and so on, I looked on the wall shear stress, and here you can see the same. For small hole diameters, you have higher wall shear stresses than for large hole diameters. And so what I computed was this epsilon, I just call it epsilon because it's short, which is just the increase of the wall shear stress from 10 millimeter upstream of the bleed region to 10 millimeter downstream of the bleed region. And here we see exactly the same. The smaller the hole diameter, the higher the increase, and the more uniform the flow field looks like. And again, this was done for different pressure ratios. We can also show the ISO lines where we have constant bleed mass flow rate. We have this trend, smaller holes are better, and again for all the different parameters. And this is all not considered in lead models. So of course I have to validate what I found. So we performed wind tunnel experiments in our S8 wind tunnel, supersonic wind tunnel for Mach 1.6 test section. We have two porous plates, two different porous plates we can install. I focus only on the one with small holes. The span is 2/3 of the wind tunnel span. And we can vary the bleed mass flow rate by just using a shocked throat. And we have pressure tabs along the plate and inside the cavity to also obtain our pressure ratio. We performed also LDV measurements and background-oriented Schlieren. And just to remind you, this is how the flow field looks like in the simulations. This is the experimental flow field with Boss visualization. We have an expansion fan trailing shock, same. And we even see faintly that we have here some expansion fans and barrier shocks. So we have some wavy topology, I would say, like this. But of course, we want to go a bit more quantitatively in the comparison. So first, we measured the upstream profile and compared it to the CFD, and it fits quite well. In the CFD, it's slightly fuller, probably because we have no roughness effects in the CFD, of course. And then we checked downstream, first for a very low bleed rate, where we have quite good fit. Still in the CFD, it's a bit fuller, but I think it's just an artifact of the inflow condition. And also for higher suction rates, we see a very good fit. So we can check what's the influence on the suction rate on the boundary layer. Here our inflow profile, if we suck just a little bit, we see that we have an increase of the momentum in the vicinity of the wall. Then with lower plenum pressure, we increase the effect, and at some point we have a saturation because we reach choke conditions of the holes, and then of course we cannot remove more mass. If we look now on the CFD, we obtain exactly the same trend. So we have a very good fit. And I would say our simulation setup is validated. And now the interesting part, the finding of the new model. And the first idea was like, how can I mimic all these different parameter influences? And yeah, it's very hard. So I checked first, like just to show you how I extracted it in reference simulation. I defined an area which is proportional to the porosity ratio and extracted my wall quantities by averaging the values in this area. And then I extracted my bleed rate by just integrating the momentum passing the hole, like the center at the hole. In the bleed model, we just want to have a very simplified mesh that everyone can apply. And the idea was here that I use the same approach of extracting the wall quantities only around the holes. Then I find my magic function and I apply the bleed rate just in the center, like where the hole would be placed. And so I can model my geometrical parameters without find a very good regression, I would say. But still, I found a regression, but since it is not published, I have to apologize that it's without values, but I can nevertheless tell you a little bit. So this is like the general trend, just to show you. This is the amount of simulations. Actually, it's even more, but I have no more place on my disk. So this is like the newest simulations I performed. And then I checked. I performed simulations for subsonic inflow conditions and supersonic inflow conditions. And just from the wall quantities, I'm able to distinguish more or less if my flow is subsonic or supersonic, because then the flow, or like the flow inside the holes, is completely different. And so my idea was I just make two regressions, one supersonic regression, one subsonic regression, and then between I have my transitional area where I just make like a mix out of both, a weighted mix. And in 3D, this is how the bleed model looks like. So I can, like the height is more or less the bleed mass flow rate. And you can see the bleed mass flow rate is higher in the subsonic region. And now we come to the implementation. And as a reminder, this was the benchmark. So the reference simulation and the model of Slater. So I would like to be very close to the gray one and better than the red one. And this is the new model applied. So you see it fits quite well. If we look at the wall mass flux, And also, if we look on the boundary layer profile, we have a way better fit. It's still some overestimation of the effect, but it's way better. And if we look globally on the difference in the Mach contour, yeah, as I told you, still downstream, we have a slightly higher momentum close to the wall. And here what you see is just that I don't model the exact position of the barrier shock. And therefore, the barrier shock is a bit downstream move, and that's the difference. But to compare, this is this later. So I would say it's a good improvement. And we can now also look on the other quantities like the wall pressure. So the wall pressure is very well reproduced by the boundary layer, by the boundary condition. And very interesting is also the wall shear stress, since in the reference, like in other boundary conditions, the suction is quite uniformly applied. We have a complete overestimation of the wall shear stress. And with the new approach, we are quite close to our reference simulations. And yeah, just to conclude, so what have I shown? That existing models overestimate the effect of the bleed on the boundary layer, which is not very good if we want to investigate shock boundary layer interactions, because we have a very full profile. Of course, the shock boundary layer interaction looks not the same. We can say that geometrical parameters must be included and considered into new model approaches. And we have now a new model, which fits very well. And what I didn't say, the computational costs are way lower. So the simulation here shown was like 10-15 minutes. The reference simulation was 5 to 10 hours on 2 times the number of nodes. So the computational costs in terms of CPU hours is decreased by a factor of 100 to 200. And just as a spoiler, it's also working for shock boundary layer interactions. So this is model versus the reference simulation, and you can guess which is the right one. Thank you very much for listening.